Hello dear friends, a great welcome to this series on engineering mechanics. Myself is Jayarajan P. This is class 10 of the series and it covers the following topics. 1. Moment of a force about an axis in vectorial format. And second, it also includes solved examples relevant to this topic. So let us start our class. So let us start our discussion on the moment of a force about an axis in the vector format. So in order to explain the concept, the same example of a car tire that is fitted with a lug nut is shown here. As you can see that it's the same range. Vector F is applied at one end of the handle and O is the lug nut and this is my y-axis. And referring this sketch, we know that in the vectorial format, the moment produced by vector F about the point O, that is the total moment by force vector F at the point O, can be written as vector MO is equal to R cross F. So this is what is written here. To find the moment of a force F about the y-axis. So what exactly we want to calculate is, we are interested in calculating the moment of the force produced by vector F about the y-axis. So here the procedure is very simple. So first we select a point on the y-axis. In this specific case, the point is chosen as O for our convenience. Then what we do is that we compute the moment of this applied force F about this point O, which is on this axis Y. And obviously we know that this computed moment at the point O due to the applied force F will be vector MO is equal to R cross F, where R is the position vector drawn from the point O that is selected on the y-axis onto any point on the line of action of the force F. Now as you can see that the moment vector MO at the point O, it will be normal to the plane containing vector R and vector F. It should pass through O and its sense should be determined by the right hand rule. So the direction and the sense of vector MO is given here. Now as already discussed, we know that this total moment vector MO, it is not fully effective in rotating the lug nut at the point about the y-axis. So accordingly, to find out the useful moment which is effective in turning the lug nut, we need to calculate the component of this vector MO about the y-axis. So this can be easily obtained using the dot product operation, which was one application relevant to the dot product. How do we obtain the component of vector MO about the y-axis? This can be obtained as the unit vector along the y-axis, that is J dot, this vector MO, that is R cross F. This is what I have written here. That is MY, that is MY means it is the magnitude of the component of vector MO in the y-axis or along the y-axis. It is obtained as J dot R cross F. Remember here, J is the unit vector along the y-axis and R cross F indicates the total moment computed about any point O on this axis. Now based on this understanding, let us evolve a procedure to find out the moment of an applied force about any axis given in the space. In this example, please refer, we were discussing about the computation of the moment about the y-axis. So instead of y-axis, let us choose any arbitrary axis in space. This is what is being demonstrated here. Look here, this is a rigid body. And this rigid body is subjected to a vector F. And here is defined an axis A. And the direction of this axis A is denoted by the unit vector UA. So now we would like to calculate what will be the moment produced by vector F about the A axis. So the procedure is very simple. First, select any point on this axis. You can choose any point on this axis A. For example, here I have chosen the point O, and then obtain the moment of this applied force vector F about the point O on the axis A. Obviously, we know that this vector MO is nothing but R cross F. And here in the gray color, I have indicated the plane containing F and R to enable me to mark the vectorial representation of vector MO. Obviously, as per our discussion, we know that this moment vector MO calculated at the point O on the axis A, it is normal to the plane containing vector R and vector F. Further, this moment vector should definitely pass to the point O, and in addition, the sense should be determined, or the direction should be determined by the right hand rule. For example, we know that from the sketch, that is FO will produce some kind of an anticlockwise moment. So if it is an anticlockwise moment, it produces about the point O. Obviously, it should be directed away from the point O as per the right hand rule, right? Now what we need to do is, we have a moment vector MO. We would like to simply find its component along the axis A. It's a very simple problem. Now it's a very simple problem. So what we do, in order to find out the component of vector MO about the axis A, which I have denoted as vector MA, how do we obtain it? Simply, vector MA, or the magnitude of the component MA, can be written as the dot product between the unit vector along the axis A and the vector MO. So this is what is being written in this sketch, that is MA. MA is the component of or the magnitude of the moment produced by the force F about the axis A. MA is nothing but it is the magnitude of the moment produced by the force vector F about the axis A. It is equal to vector UA. What is vector UA? It is simply the unit vector defining the axis A dot R cross F. F, it is a very common symbol for us. It is a force vector in the Cartesian format. And what is R? R is the position vector that is drawn from any point on the axis A to any point on the line of action of the force F. So you can choose any point on the axis, and from this any point on the axis you can draw a position vector to any point on the line of action of vector F. Please remember, this is a dot product, so accordingly the answer is a scalar, and we know that MA here is simply the magnitude of the moment produced by vector F about the axis A. Now once we know the magnitude of this moment about the axis A, we can simply express MA in the vectorial format as vector MA is equal to its magnitude, that is MA into the unit vector along axis A, that is UA. So the calculations are very simple. So normally we call this operation. So here you will find that there is a dot operation and there is a cross product operation. So this combination of this vectorial operation, we call it as a scalar triple product. Now let us find out how to evaluate this product, okay, in a simplified way when the unit vectors, position vectors and the force vectors are available in the Cartesian format. So we know that MA is equal to, let us assume that vector UA, that is a unit vector representing the axis A, can be written as UAXI plus UAYJ plus UAZK dot. We know that vector R cross F can be put in a determinant format as IJK, Rx Ry Rz and Fx Fy Fz. Now it is possible for us to simplify this determinant and then carry out a dot product. Now simplifying this expression, we obtain the result MA as UAX into Ryfz minus RZFy minus of UAY into Rx Fz minus Rz Fx plus UAZ into Rxfi minus Ryfx, which can be conveniently put up in the form of a determinant as MA is equal to UA dot R cross F, that is UAX, UAY, UAZ. Remember, UAX, UAY and UAZ are the components of the unit vector defining the axis A. Rx, Ry, Rz are the components of the position vector drawn from any point on the axis to any point on the line of action of the force F, and Fx, Fy, Fz as usual are the components of the force F. So this is how you can easily calculate the magnitude of the moment of a force about an axis. Once you know the magnitude, it is very simple. You can also express this moment in a vector Cartesian format as vector MA is equal to its magnitude MA into UA, vector UA. So now, please remember one important thing. If the magnitude of MA happens to be negative, it means that its line of action, its direction will be opposite to the direction of the unit vector. Or if MA is positive, it does mean that the moment vector calculated on the axis A, it will be directed in the same direction of the unit vector. Okay. Now, in order to explain our discussions, let me just take a very simple example, that is example number 2. So let me read this problem statement. Determine the moment M may be produced by the force F as shown in the figure, which tends to rotate the rod about the AB axis. Look here. So this is a simple case of a bended bar. You can say that it consists of 3 straight segments and this rod assembly, it is affixed to the XY plane using 2 clamps. And the end of this bar assembly is subjected to a force of 300 Newton at the point C. And as obviously seen, we know that the effect of this force F is to rotate the entire assembly about the AB axis. So we would like to find out what will be the turning effect produced by this force F about the AB axis. So let us proceed for our calculation. Now we know that as discussed in the vector approach, the moment produced by F about the axis AB can be conveniently calculated as MAB is equal to UAB, that is the unit vector along AB dot vector R cross F. Please remember that vector UAB is the unit vector defining the direction AB axis of the rod, which can be easily computed from the non-coordinates of A and B. Please remember that the origin of this Cartesian system is placed at the point A, so that its coordinate will be 0, 0, 0, and B is having a coordinate of 0, 0.4, 0, 0.2 and 0. So accordingly, we can easily obtain the unit vector along AB as the position vector directed from AB to the magnitude of this position vector, which is equal to 0.4i plus 0.2j divided by its magnitude, which is square root of 0.4 square plus 0.2 square. That is 0.8944i plus 0.4472j. So we established the first term. Now let us talk about vector r. Based on our understanding, we know that vector r is the position vector drawn from any point on the axis to any point on the line of action of the force F. So in this case, what we can do is we can either draw a position vector from the point A to the point C, which satisfies our definition of RC, because A is a point on the axis, again C is a point on the line of action of vector F. Again, we know that vector RD also satisfies our criteria because it is again drawn from a point on the axis AB to a point D on the line of action of F. Please remember that this force vector is applied. That means this straight segment is exactly in the plane YZ, is in the plane XZ. Means that the projection of this force onto the x-axis, that's a point D, also lies on its action. So for this calculation, to represent vector R, we can use either vector RC and vector RD. So in this case, what we did is we have simply used vector RD. That will be convenient and easy for our calculation. What is vector RD? It is position vector of D minus position vector of A. That is obviously, we know the coordinate of the point D. What is that? It has got a x coordinate of 0.6, and it is in the xz plane. Accordingly, we know that the point D here, it is on the x-axis is y and z coordinate should be 0, which means RT can be put up in the vectorial format as vector RD is 0.6i. And vector F, obviously we know that it has got a magnitude of 300 Newton and it is directed downward in the minus z direction. So vector F can be written as minus 300 K. So now our task is simple. MAB is equal to vector UAB dot vector RD cross F, which can be conveniently put up in a determinant format. So the first row being the coefficients of the unit vector, vector UAB, which is already calculated here. That is 0.8944 and 0.4472. And the K component is already 0. And vector RD, it has got only the coefficient for the I. So we write it as 0.600. And vector F, it has got only a K coefficient. So 00 minus 300. So we find that the magnitude of the moment calculated about the axis AB due to the applied force F is equal to 80.5 Newton meter. It's a scalar product. It has provided us magnitude of the moment. Now, how to express? We know the magnitude. How to express this moment about the axis AB in the vectorial format? Because we know that the moment of a force calculated about an axis is a vector. So obviously we know that vector MAB is its magnitude, that is MAB, which is already calculated as 80.5 multiplied by the unit vector along its direction. What's the unit vector along its direction? That's the unit vector along the axis AB. So substitute it, 80.5 into the unit vector along AB is 0.8944i plus 0.4472. That is 72i plus 36j Newton meter. So this is the vectorial representation of the moment of the force F computed about the AB axis. So that's all about our discussion on this class. So we'll come up with a new topic, that's a couple and a couple moment in the next class. Till then, bye.